So, in the previous lecture we started our topic of magnetization in materials. If you have a material, it's made of atoms or molecules or ions, and there are materials for which this basic constituent that I am calling atom is not having any dipole moment, magnetic dipole moment, because of the atomic electrons. The electrons which are there in the atom, they all have magnetic moments because of the spin and also because of their motion around the nucleus. But then since there are too many electrons, several electrons in the atom, most of them pair up and cancel their magnetic moments. But then for some materials you have unbalanced magnetic dipole moment of the atom. So, you can look at this atom as a current, and to some extent yes, since the electrons are motion, it is a current. But then also remember that you can have that spin also involved, and this motion classical electromagnetism cannot be used there because these are very small quantities. But nevertheless there is a current, and that current you can at least say that for magnetism purposes this atom can be represented by a current which is going there, and that current will have magnetic moment, current times area of the current loop, and so that is how these magnetic moments are created. Then we talked of paramagnetic materials, where you do have atomic magnetic moments, and but they are all independent of each other. Thermal motion is there. If you apply a magnetic field, each one slightly orients towards this external magnetic field and gives you a net visible magnetization. Now, under this category we also said there are some materials where the neighboring atoms interact in such a way through the overlapping electrons, which we know as exchange interaction, so that atoms by themselves they try to align the magnetic moment in the same direction. So, that is how lot of atoms are able to do that, and that makes a domain. So, in a given material you may have several domains here, 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 here. This a somewhat smooth transition at the boundary. If you have one domain here and one domain here, it's not a absolutely sharp that okay, all these moments are here and suddenly they are there. So, that we call domain wall. And if we put the material in a magnetic field, a small magnetic field, then this field tries to orient the dipole moments in that domain wall, so that the domain wall itself is shifted. The magnetic moments which are aligned, which are in the direction of applied magnetic field, they grow in size. The other ones which are much deviated, they shrink in size, and you get a very good a large magnetization that we call ferromagnetic materials. In the same category like chromium, we have materials where the neighboring atoms try to misalign. Misalign means anti-parallel alignment of the magnetic moments. So, those kind of materials are also there. All our bar magnets which we use in laboratories are made from ferromagnetic materials. So, at the atom level, this magnetic dipole moment is equivalent to a current there in the atom, and to some extent that current is real also, to some extent at least. But then at bulk level, we have a magnet in our hand, a 10 centimeter magnet in our hand, or some kind of disc in our hand which is a magnet or which is magnetized. Then can we still talk in terms of those currents which are there, atomic currents which are there, which are making this whole material? So, that will be the topic of today. So I will start with a disk. I will start with a disk. Let us say we have some kind of a disk. Some kind of a disk. This is the top surface of the disk. This is the top surface of the disk, and let us say this is y-axis and this is z-axis. In x-axis is perpendicular, and this is that thickness. This is that thickness. So this x-axis will be in this direction, right? So this top surface is this xy plane, and the thickness is in x direction. So you can think of this as the material, this as the disk, and then here is your y-axis, and if I take it horizontal, this is y-axis, this is z-axis, and this thickness is z-axis. So that is how, suppose we put our coordinate system, and then this is, let us say it has a uniform magnetization. M, which is a constant m, and then in k cap. So along this thickness you have magnetization. In what way we produced this magnetization is not the topic of interest now. It is magnetized. Given that we have magnetized it, and everywhere the magnetic moment is per unit volume is this m, and the direction is perpendicular to this surface. So this is the situation. Now the magnetic moment of this whole thing will be this magnetization into the volume. So dipole moment, magnetic dipole moment of this whole disk. This will be mass times area, this whole area, and then this thickness here, this thickness. Say this thickness is, let us say, T. So this magnetization, area, and into T. So this is volume. So magnetization times volume is the total dipole moment. It's uniform magnetization we are assuming. So that is how the magnetic dipole moment will be there. Now suppose we pass a current, we say that all right, we forget about magnetization. Suppose we say that along this thickness there is a current. Along this thickness there is a current. So along this thickness there is a current. So it becomes a current loop. All right. So in our case, I use this diary. If this is the disk, and then there is a magnetization, uniform magnetization in z direction, we say that forget about magnetization, and suppose there is a current here, current here, current here, and current here, a current loop, this current loop. So if the current is I and this area is capital A, the area enclosed by that current loop is capital A, which is area of this top surface here or bottom surface here. So if I have that kind of current, then we can ask what is the magnetic dipole moment of that current loop. So magnetic dipole moment of the current loop will be current times area, and in k cap direction, Now if I equate these two, what I get? I is equal to m times T. So m is given to me, thickness is known to me, I calculate what is the current, and I say that if I only consider this current here, it will have the same magnetic dipole moment as it is given to me that it has a uniform magnetization capital M, and then therefore there is a magnetic dipole moment. So I can I replace this whole thing, this whole magnetization by this single current loop? So that is a question. Now it's not very obvious. Yes, the magnetization is same and the dipole moment is same, and therefore at large distances, yes, possibly yes. This is if this thing is small, then possibly yes, but close to this disk, it's not very obvious. But very interestingly, it turns out that yes, you can do it for any distance. And how do we reach that conclusion is will be discussed now. So the whole thing was that, okay, the current is there, but then it is made of this, there is no real current here, we are assuming an equivalent current. But if you consider this as a combination of small chunks, you draw lines on this surface parallel to y-axis, and then parallel to x-axis, and then cut this disk thickness t, you will get kind of rectangular cubes, not cubes but rectangular objects. Okay, so this is, let us say, some length, this is some length, this is, let us say, the length is dy, this length is dx, and the thickness is t, so dz is t. So you will have a rectangular object dy, dx, and dz, which is t. Just consider one such element here, and to assist you in this imagination, I have something on my table. Perhaps that will help you to understand what I am saying. So let us say this is a disk. And the surface here, I can draw x-axis and y-axis, and then z-axis will be perpendicular. Okay, so that is the case. Now what I do is I draw lines. All right, so I draw lines here like this. I am cutting the slices. And then this way perpendicular along the x-axis and along the y-axis. All right, as you cut the birthday cake. Okay, so this is the kind of structure I have made. Now I pick up one such cube. I will separate everything and pick up one such cube. So let me do it this way. And let me pick out one such cube here. All right, so I have picked up one. From where I have taken it? From here. Remember, this is a material, magnetized material, magnetization in the z direction. And now this particular piece, which is dx dy dz, the volume is dx dy dz, this top surface is dx dy, and this height is dz. So I draw current lines. Let me put an arrow here, and this is one. Then here that same current continues here, that same current continues here, the arrow is like this, the same current continues here, the arrow is like this, and then the same current continues here. On this part the arrow is like this. So, this is a rectangular current loop, current going this way, this way, this way, this way. Looking at the top, it is anticlockwise, its magnetic moment is upward. And how much is that magnetic moment? That magnetic moment is capital M and multiplied by the volume dx dy dz. And if I say that this current I is such that it has the same magnetic moment, then we will have I and then into dx dy as the magnetic dipole moment, and if I equate these two, I can write what is this I. So, there is a current, and this is a somewhat real, not exactly real, because yes, it is because of the atomic. You can do similar thing in each of the cube, So, I place it back at its place and I take the adjacent ones, I take the adjacent one. So, I have put the original one here, and then this I have picked up from here, and I do the same exercise. There is a current out here, this is the direction of arrow, exactly the same way, replica of that. I wish I could have this copy paste Control C Control V facility here to replicate this everywhere. All right, so I just place it back, and then I am picking the two together. These two I have picked together, and now look at the current at the interface where these two are touching. Look at the current direction here, and look at the current direction here. Okay. This is the situation, this is how I picked it up. You can again see this is an anti-clockwise loop, this is also an anti-clockwise loop. See, identical, this way, and then it goes this way, But when this was placed together with this, what are the directions of the currents at the interface? Cleanly watch the two arrows. They are in opposite directions. We made these loops in identical fashion. If I look at this particular loop from top, it is anticlockwise. If I look this from the top, it is anticlockwise. So, we have made this in identical fashion, but once they are here, then you can see that the two arrows are in different directions, opposite directions, like this current and this current will make it 0. Okay. So, everywhere if I do the same thing, here, because this is also magnetized. So, for this also I can write the current, anticlockwise current, then at this interface also the arrows will be opposite. At this interface also the currents will be opposite, at this interface also the current will be opposite, at this interface also the currents will be opposite. No current here, no current here, no current here, no current here. If I just pick one, yes, there is a current I, and I into dx dy is the magnetic dipole moment, which I will equate to capital M into this dx dy dz. There is a current, very much current, but then when I look at the whole thing, whole material, not just one chunk, then I find there is no current here, there is no current here, there is no current here, there is no current here. And similar is for all the cubes. There is no current here, 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 there is no current here. But you talk of any one, there is an anticlockwise current around this periphery. Now what happens to this particular one which is sitting at the end? Suppose I take this particular one, this particular one. Now in what, how do I, this is also magnetized, this also has a magnetization, a dipole moment. So this also has a magnetization, and the magnetization is in the upward direction. So this is also equivalent to a current loop. So I can draw the current this way. So I draw the current this way, anticlockwise of course. Here the current is going in this direction, then here the current is going in this direction, and here the current is going in this direction. It's bending is this way, and the finally the loop is completed. Now let me place it back. Let me place it back. How was it? It was like this. Let me place it back. Was it this way or it was this way? Yeah, I think it is this way, right. That makes the surface. So I place it back. Once again you can see the current goes this way, then goes this way, and then goes this way, anti-clockwise current, and I place it back here. Now this current and this current, they are adjacent surfaces. So the current here and the current here will be opposite. This is anti-clockwise going this way, this is anti-clockwise going this way. So here the total current is 0. This and this is adjacent. Here the current is this way and here the current is this way. So no current here, no current here, but here this is not cancelled by anyone, nothing on this side. So this current will remain there. So if I look at the entire thing, no current here, 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 but here there is a current, here there is a current, and similarly if there is a current here, there will be a current here, okay, there will be a current here this way, 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 and so on. So you can see that in this entire material, now I am not saying that I am taking current at the periphery, I am taking current everywhere inside the material. All these chunks, all these rectangular objects, they are of identical type. So nothing special about here or here or here or here, everyone is magnetized, everyone is magnetized. And I am not saying that I am taking the current only at the periphery, I am taking current everywhere in the whole material, but then I find that when I do that, each small element in the material, when I replace it by a current loop there, I find that on the periphery there is a current. See the arrows, on all the periphery there is a current this way and no current inside, okay. So these atomic currents which are there, you can think these as atom by atom also. If everything is aligned like a ferromagnetic material, everything is aligned, you can think each one of these as one atom, and that atom is a current, and then so many atoms are close to each other. So wherever the interior, they cancelling, the neighboring currents are in opposite direction, but at the periphery you do have a current. And come back here on the board. So, this magnetized material is not only equivalent to the current, but it in some sense it is a real current here. Okay, it is a real current here. So, this whole magnetization produces a current of this kind. When you magnetize the material, if you do not magnetize and then the atoms are randomly oriented or domains are randomly oriented, then there is no current here. But when you magnetize it, when you bring this magnetization, then on the periphery you have this current. How much is this current? That we have already done. I is equal to m times T, that is m times dz. This is the current. Now, this current is known as bound current. This current is known as bound current. Why? Because although you can see that there is a current at the periphery, but no electron is going from here to here to here to here or here to here to here to here to here to here. The electrons which are here, they are not coming here, they are not coming here, they are not coming here, because all these electrons are bound to their nuclei. All these electrons are bound to their nuclei. In any chunk, in a particular chunk, you can see that the electron is only moving here, close to that nucleus. Okay. So, every electron is bound to the material, but still you can see that okay, ultimately I have a current here. So, this is known as bound current, and in this particular case this bound current is only on the surface. This is the surface. Okay, this is the surface. You can see on this our this roti is also, this is the surface. This whole thing one material, one chunk, place it back, one material, and here is the surface, and the current is only on the surface. If you take the directions, this m is in z direction, and then you have this x direction and y direction on the surface. If you are here, somewhere here, let us say on this thickness, and draw a perpendicular to this, it will be like this. Okay. So, the perpendicular is like this, this perpendicular, here this is perpendicular, here this is perpendicular, here this is perpendicular, and see what is m cross, what is the direction of m cross n cap, m cross n cap, what is the direction of this. So, look at this, the n here is this way, this is n cap, normal, perpendicular to the surface, this is this, and m is vertical, and I am asking, so m is this, yeah, I have this facility, alright. So, this is m, this is m, and this is n cap, and m cross n cap. So, m cross n cap, it will be perpendicular to both and going in this direction. M cross n cap is this direction, and that is the direction of the current anywhere on the surface, anywhere. If you are here, this is the perpendicular, and this is the direction of m, and m cross n will be perpendicular to both and going this way. So, this is giving me the direction of the current. And what about magnitude? What about magnitude? Magnitude is m times dz, the current is m times dz. So, this is the magnitude here will be just m, the magnitude of this will be m. This is surface current, remember, this is a surface current, therefore, you can ask for surface current density. How do I calculate surface current density? If there is current on a surface, then perpendicular to the current on the surface we draw a line, and then ask how much is the current crossing divided by the line, length of the line, that is the surface current density. That is how we define. If you have a surface current like this on this surface, then I say that okay, draw a line dl and see how much current is going through this dl, and that current divided by that length, that is known as surface current density. So, here the current is m times dz, the current here is m times dz, and dz is this length, dz is this length, and therefore, the current density, surface current density, is k which is or first magnitude, this m dz and divided by dz, that is m, that is m. So, the current density is just k, and the direction as you see is in this direction, m vector cross n vector direction, and the magnitude is also same, the magnitude of this m, and that this m is k. So, the magnitude of m cross n cap is k, the direction of m cross n cap is the direction of this surface current density, and therefore, we can write k is equal to m cross n on the surface of the material, of the magnetized material. If you talk of this top surface, even there this formula will work, because here on the top surface, when you draw the perpendicular normal, it will be in the z direction itself, and therefore, this m cross n cap will be 0, m is also in z direction, n cap is also in z direction. So, that will be 0, no surface current here, the surface current is only here. So, I can say that on all the entire surface of the material, here, everywhere, this formula works. Kb, B I am writing for telling that this is a bound current. In contrast, when you put a battery and supply electrons in the circuit, then these electrons go around the circuit and come back to the battery, that we say free current. It is not bound to atoms, the electrons are not bound to atoms, but here the electrons are bound to atoms, still they are giving a current. So, we call it surface current density, bound surface current density. So, it is bound surface current density, alright. So, this is bound current, and then one part is the surface current. So, we call it bound surface current density. This is our Kb, this is our Kb, and this is m cross n cap on the surface, where n cap is the perpendicular normal unit vector along the perpendicular along the normal to the surface, and m is the magnetization vector at that point. So, that is how this Kb is defined. Now, this is good, very nice, but then this magnetization, if it is not uniform, if this magnetization depends on location, here the magnetization is different, here the magnetization is different, then what will happen? Then what will happen? And what will happen is that if I take two adjacent these the pieces from here, let us say these two or any two adjacent pieces. So, let me separate it a little. And take two of them, instead of one, take two of them. So, these are the two. Now, if I separate them, these are the two, the adjacent ones. For this I will draw a current, magnetization in this direction. So, the current is here like this, the current is here like this, the current is here like this, and current is here like this. So, I have this loop, fine, good. So, I place it here and then I take the other one. Once again the current is in this direction, the current is in this direction, and so on. But now, since the locations are different, and M is not uniform, and we assume that it is changing in this direction. As I go from here to here, M is changing. Magnetization is vertical, but the magnitude here and magnitude here is not equal, it is not uniform. That means the current that I have drawn here and the current I have drawn here are not equal in magnitude. Magnetization is more here, then this current will be stronger. The magnetization is less here, this current will be smaller in magnitude, and if we are putting them together, although the directions are opposite, you can see that the directions of arrows are opposite. This arrow is pointing this way, this arrow is pointing this way, but then the magnitudes are unequal and you have a current in the interior of the material. So, this was the case when the M was uniform, the entire current was only on this periphery, only on the surface. But if the magnetization is non-uniform, you can have a current even in the interior of this material. So, that we will discuss next lecture.